special RI seminar. Today we are very happy to have our speaker Chung-Wei Lin, Professor Chung-Wei Lin from National Taiwan University, the Department of Computer Science and Information Engineering. Professor Lin got his PhD from UC Berkeley in 2015. And after that, he spent 3 years in Toyota Info Technology Center as a researcher. And he joined National Taiwan University last year. Yeah. And Professor Lin's research interests include cyber-physical systems, connected and autonomous vehicles, security, system design methodology, and model-based design. And today, his topic will be modeling, design, and analysis for intelligent vehicles, intersection management, security-aware design, and automotive design automation. So let's welcome our speaker.
Okay, so thank you for the introduction, and thanks for coming. So today I'm very happy to share some of my research with you. So as Chung-Liu introduced that I joined NTU last summer, so today I will provide some high-level overview of the research I have done in the previous few years, including some of them are actually done in Toyota. So, but don't worry, there's no confidential information. All of them are based on published work. Okay, let's show this video again. I just tested and I found this lag a little bit in this mode, so I switched to this mode. So, yeah, I really like this video because if in the future all cars are connected and autonomous, maybe we can reach this kind of intersection that vehicle can go through the intersection with in a very efficient way, and there's no collision. So that's something we really want to achieve in the future. But here we want to emphasize that we probably need both connectivity and autonomy. So this brings two questions first. The first one is, what if the intersection management does not have connectivity? Means all vehicles are autonomous, but they cannot communicate with each other. So I think the answer to this question is quite trivial, that the sensing capability of each autonomous vehicle is actually very limited. Yeah, if there's a building in the corner of the intersection, they cannot see or sense another vehicle coming from the 90-degree direction. So that's the reason we can use connectivity to provide more information. With more information, you can achieve the intersection management better. So the other question is, what if there's only connectivity but there's no autonomy? That means although we have a lot of information, but the driver is human driver, it's not autonomous vehicle, then the problem is human driver, they cannot provide very precise control. Yeah, if the intersection manager tell you, please enter the intersection after 5 seconds, do you think you can do that? Sometimes it is very difficult. Of course, another problem is maybe you want to enter the intersection earlier. They will not follow the instruction from the manager. So that's a reason. I also think this is a very good example that when we talk about intelligent vehicles, usually we want to emphasize that we want to have connectivity, but also autonomy. And then with both of them, we can have a very good solution to no matter intersection management problem or other application. Okay, so I think everyone is quite familiar with autonomy. So autonomy or autonomous vehicle, the goal is maybe you want to go to a destination, you get on the car and you can start sleeping. So that's quite a trivial use case. And then for connected vehicle, we can talk about more application. For example, CSIE, we will talk about CSIE later, or emergency vehicle warning, and it's like side road merging and sharp curve assistance. So talking about emergency vehicle warning, let me show some video again. This is mainly to show the advantages of connected vehicle. So one day you are driving your Lexus and there's a right turn. So this is a scenario I just mentioned. There's a corner, and there's a building at the corner. And you make a right turn, suddenly you see a fire truck coming and there's a collision. So if we use another point of view, this is, this blocks the sensing of the vehicle. Yeah, and after the right turn, you cannot see you find the fire truck is coming and there's a collision. And if we can utilize connected technology, then we can relay the message that the fire truck is coming. So we can take this video. So, oops. Okay, we need to go to the full screen, but it's lag a little bit. Okay, the fire truck is coming. They can inform this vehicle, say I'm coming, and this vehicle can inform this one, so that this vehicle can go right as early as possible, and there will be no collision. So that's another example, a very simple example that connectivity can help in some cases. Okay, so this is very basic introduction. Today I will cover 3 main topics. The first one is graph-based intersection management. So we focus this specific application, intersection management. Then I would like to talk about security. So when cars become connected and autonomous, this becomes a chance or opportunity for hackers. So what we can do to protect against hackers, that's something I would like to discuss. The last one is automotive design automation. Because systems become more and more complicated, we need some design tool to help us to design correct and safe automotive system. That's the main topics I would like to cover today. Okay, let's start from intersection management. So the setting of intersection management is we are thinking a centralized solution, means there's an intersection manager, or you can think it's a roadside unit. So vehicle will provide information to the intersection manager, and the manager will receive those information, do some scheduling, and tell those vehicle what you should do. For example, please enter the intersection after 5 seconds, and so on. Okay, of course, there can be some distributed solution, but in today's talk, I will mainly talk about centralized solution. Okay, and we assume all vehicles are connected and autonomous. Of course, if some vehicles are not connected or non-autonomous, things will become very complicated. In this case, it's just a starting point. We can assume all vehicles are connected and autonomous. And every vehicle has a fixed trajectory. Means if I'm this vehicle, I want to go to this lane, I will follow this trajectory. And they will not change the lane or do some like passing other vehicle or something. It's a very simple scenario. Okay, we model an intersection by conflict zone. Okay, so our initial work, probably 2 years ago, actually worked with Professor Liu, that we model the intersection as one conflict zone. But we found that actually we can model the intersection into multiple conflict zones, like 4 conflict zones, 16 conflict zone, and this one I think is 24 conflict zone. The definition of a conflict zone is at the same time there can be only one vehicle inside the conflict zone. Okay, you cannot have multiple vehicles in a conflict zone. So here, given one problem instance, we can build a timing conflict graph. Okay, timing conflict graph. So this graph, okay, the vertex set is a subset of the product of the set of vehicle and the conflict zone. For example, given this problem instance, we can have 8 vertices. For example, vehicle 1 go through conflict zone 1, 2, 3. So we have vertex 1, 1 means vehicle 1, conflict zone 1, vehicle 1, conflict zone 2, vehicle 1, conflict zone 3. And then we can do the similar thing for vehicle 2, vehicle 3, and vehicle 4. So we have this vertex set. And then we have type 1 edges. So it means same vehicle's trajectory. In this example, means vehicle 1 will go through conflict zone 1, 2, 3 in this order. Okay, it must enter conflict zone 1 first, then conflict zone 2, then conflict zone 3. And a similar thing, we can apply it to vehicle 3 and vehicle 4. And then we have type 2 edges. In this case, means from 1, 1 to 2, 1, means vehicle 1 must enter conflict zone 1, then vehicle 2 can enter conflict zone 1. And this is because they are from the same lane, and we don't allow passing or something. So we can guarantee that this event will happen before 2, 1, this event. Okay, so far it's straightforward. And the problem the most challenging part is type 3 edges. Means there's a conflict between several events, but we don't know which one should happen first. For example, 1-1 and 4-1. Yeah, in this case, we can schedule vehicle 4 to go through conflict zone 1 first, or vehicle 1 to go through conflict zone 1 first. But this is our choice. In this design optimization problem, we can pick. We want to do some scheduling to pick which event to happen first. Okay, so this is timing conflict graph. We will talk about how we handle this graph. Okay, but before that, let's talk about the modeling expressiveness. Why we want to model an intersection into multiple conflict zones. Okay, this is one example. If we model this intersection as one conflict zone only, okay, then one solution is, let's say vehicle 1 go through the conflict zone first, and then vehicle 2. Okay, and it's trivial that if we can model the intersection into 4 conflict zones, actually these 2 vehicles can go through the intersection at the same time, like this. Okay, so you can see that if we have more conflict zone we model the intersection as more conflict zone, we can have larger solution space. So that is good for solution quality. Of course, maybe there is some computational overhead. Okay, so I think we have published this paper, so actually I simplified something. So we have some parameter to calculate the timing to enter a conflict zone, the timing you need to go through a conflict zone or travel between conflict zone. I ignore that. If you are interested in that, you can definitely contact me. We can provide a paper or presentation slides. Okay, but in short, the problem here is it's a cycle removal problem. If there's a cycle, means you don't know how to decide the order of those vehicles to go through this intersection. So the basic concept is we want to remove cycle from the graph. And we want to minimize the pacing time of the last vehicle, means we want to process all vehicles. And we also want to minimize the average delay of vehicles. Okay, and there are 2 guarantees we would like to provide. The first one is, of course, we want to guarantee there's no collision. We don't want to schedule 2 vehicles enter the same conflict zone at the same time. But this thing is implied by the acyclic graph. I mean, if you have a cyclic graph, somehow you can decide the passing order so that we will have no collision. And the most interesting part of this work is we want to guarantee there's no deadlock. So actually, the following slide we will talk about how can we guarantee that there's no deadlock. Okay? Okay, so to this point, maybe you think, okay, quite straightforward, right? So no deadlock, then I say this is a cycle removal problem. So the straightforward idea is if there's no cycle in the graph, then there's no deadlock, and then we can schedule those vehicles accordingly. Okay, that's when I faced this problem first time, I also think that is a solution. Okay, but it is not true. Okay, so let's show some example. In this example, you can see these 5 graphs. They don't have cycles, right? You check the graph, there's no cycle. But they are actually deadlock in figure A and B and C. Okay, for example, this one, vehicle 1 enter conflict zone 1 first, right? And it want to enter conflict zone 2. But based on this graph, it needs to wait vehicle 2 to enter conflict zone 2, then it's its turn. However, vehicle 2 cannot enter conflict zone 2 because it cannot enter conflict zone 1. And it is because conflict zone 1 is occupied by vehicle 1. So you can see that in this graph, there's no cycle, but there's a deadlock. Vehicle 1 cannot enter vehicle 1 cannot enter conflict zone 2. And the vehicle 2 cannot enter conflict zone 1. So there's a deadlock. Okay, this is a similar thing. Okay, vehicle 1 cannot enter vehicle 1 cannot enter conflict zone 3. And it is because actually vehicle 2 cannot enter vehicle 2 cannot enter conflict zone 1. So, okay, and this is a little bit more complicated scenario. vehicle 1 wants to enter conflict zone 3. But conflict zone 3, it needs to wait vehicle 3 to enter it. But vehicle 3 cannot enter conflict zone 2 because it is waiting vehicle 2. And the vehicle 2 is waiting vehicle 1 to leave conflict zone 1. So there's a deadlock. Okay? But these two examples, there's a no deadlock. And this one, if you compare with this, it's very similar. But there's no deadlock because vehicle 2 can wait inside of the conflict zone 2 and let vehicle 1 to go through it, and then it leave the intersection. Okay, so we can see that although we say this is a cycle removal problem, but it is not that trivial. We cannot just check this graph, or we cannot just remove edges from the graph. And if there's no cycle, we say there's no deadlock, we can schedule. No, this is not a solution. Okay, so to make sure there's a no cycle, okay, actually we built resource conflict graph. The first graph I mentioned is timing conflict graph. To make sure there's a no deadlock, we need to build resource conflict graph. So we have some construction rules. The first one is, if you have this kind of topology inside your timing conflict graph, you will build this graph inside your resource conflict graph. Okay, this is a construction rule. And then we have 4 other rules like this. If you want to have a generalized explanation, you can think we will build a vertex for each edge inside the timing conflict graph. Okay, we will build a vertex in resource conflict graph for each edge in the timing conflict graph. Okay, so of course we can prove it, but let's show the example. Okay, we build the resource conflict graph for the 5 example. Okay, and then you can see that the example in ABC, there are cycles, and the example DE, there's no cycle. And we can prove that, yes, in resource conflict graph, if there is cycle, then there's a deadlock. If there's a no cycle, there's no deadlock. So when I say this problem is cycle removal problem, somehow what I want to say is this is a cycle removal problem for resource conflict graph. Okay, so that's how we can solve the optimization problem, and we can use this approach to verify there's no deadlock in our solution. Okay, so this is graph-based verification. Actually, we have another approach to verify there's no deadlock. We use PetriNet. And we have to say that PetriNet is actually more powerful than this. Okay, but yeah, we can fit PetriNet into this use case. And then we can also verify that there's no deadlock. And the result is similar to our graph-based verification. So if you are interested in PetriNet kind of verification, I think you can contact Professor Insakam there. Yeah, I think he's very familiar with this. Okay, so in summary, this is my first topic. So I didn't cover how we solve the cycle, how we solve this problem, but it's basically a heuristic because we want to make sure the solution can be used in real time. So definitely we don't want to use 100 seconds to solve the intersection problem, right? Intersection management problem. Before solving it, you need to let those vehicles to wait in front of the intersection. No, we don't want to do that. So we prefer a very fast and a heuristic algorithm. But I didn't cover the algorithm here. What I want to emphasize still that this is a cycle removal problem, but it is not cycle removal problem on the timing resource graph. It's a cycle removal problem on the resource conflict graph. And we can use the some verification techniques to make sure there's no deadlock. So this is the one solution after our algorithm. So you can see that there's a no cycle, and if you construct the resource conflict graph, there will be no cycle. And it implies a solution like this. Oh, keep your eye on the animation. Yes. Okay, so yeah, this is basically this animation follow this conflict graph, and yeah, you can see actually this is very efficient in this case. Okay, so this is the first topic I want to cover. So far, any question? Then I will go to the next question, talk about security. Okay, so this is a screenshot from the movie Die Hard in 2007. I remember when I give a talk at another place, someone suggests me to change the picture. They say this is too old. But somehow you can say in 2007, in the movie, someone has talked about this kind of concept that in the future, maybe transportation system is hacked. Then we can create a lot of like collision or accident, so on. Okay, so one thing we are very interested in is, yes, security is not a new problem, right? In computer network, there are so many solutions or so many research talking about security. What is the difference between those kind of security and the security in automotive system? And I think the major difference is that the computational resource of automotive is very limited, and we have real-time constraint. So this is just an example that, let's use RSA algorithm to do encryption, decryption, or authentication. But the problem is, if the message is breaking your car, you don't want to use 1 second to authenticate this message. Probably you want to execute this action in, let's say, 20 milliseconds, like that. And we don't want to implement the security solution, test it, and then find it cannot fit into the system, because if you want to redesign the system, the cost is very high. So somehow this is related to the third topic I would like to cover, the automotive design automation. Somehow you would like to have some early designs, early decision in the design stage, so that you can fix the system and prevent a lot of design cost. Okay, this is another view of security in automotive system. Usually we can separate the problem into 4 layers. The first one is V2X, vehicle to vehicle or vehicle to infrastructure. So we need to make sure the security mechanism can fit existing standard like DSRC or maybe 5G. And the second layer is gateway. Gateway is between in-vehicle network and the V2V communication. So traditionally, let's say several years ago, when automotive company talk about security, one solution is, let's separate in-vehicle network and the V2X communication. For example, GPS or something. Let's totally separate them. Okay, yes, from that perspective, maybe you can provide some security, but if you consider the concept of connected vehicle, the concept is, I want to consider the information from outside and make some decision, right? If you consider this concept, then the totally separation solution is not appropriate. For example, you talk about intersection management. What I need is some information from outside to help me make decision. Yeah, so separation, then you lose the advantage of connected vehicle, right? So that's the reason if we consider connected vehicle, gateway, you cannot just separate them. You need to let them communicate, but you probably need some intrusion detection or firewalls. The third layer is in-vehicle network. So we must make sure it's very fast. It's very lightweight. And the component layer probably involves some hardware security. You need to store some secret key or need to have some hardware security modules. Okay, this is the layer view of security. Okay, and regarding security, I will cover many topics. So probably each topic just 1 or 2 slides. The first one, let's talk about timing. Okay, this is another application of connected vehicles. I think everyone knows what is cruise control, right? Cruise control means you want to maintain the speed, and the vehicle will maintain the speed, even it is going to hit the car in front of you. It will not stop. It's cruise control, just maintain the speed. And talking about adaptive cruise control, yeah, it is better than cruise control. Means I want to maintain the speed, but if I'm going to hit the car in front of me, the car will stop or decelerate for you. Okay? No matter it is cruise control or adaptive cruise control, it's only based on your own sensor. It's not related to connected vehicle, right? Then we talk about cooperative adaptive cruise control. Means the car in front of you will provide some information to you. Okay, for example, maybe it's acceleration. So acceleration or like intention, this kind of thing is very difficult to be sensed by your own sensor, right? So that's the reason we want the car in front of you provide this kind of information via V2S communication. We want the car in front of you to provide this kind of information via DSRC or 5G messages. Okay. Then we have more information. So ideally, we can have better performance of CSIE. Better means we can have a lower car following gap, and we can still guarantee there will be no collision. Okay. Then, based on CSIE, is it possible that the hacker can do something? So let's don't talk about the fake message, because maybe we can have some key authentication or PKI, some kind of system to support authentication. Let's talk about the easiest way to attack, jamming. Okay, so let's show the video again. This is our simulation on CACC. Okay, car accelerate. They will maintain the speed to, I think it's 30 meters per second, and the car following distance gap is 24 meters. And and someone will do jamming very soon. So here I want to say, probably I will disappoint you. Maybe you expect to see collision, right? Unfortunately, or fortunately, there's no collision. But you can observe that the car following gap is much longer. Okay? So this is the result if someone is doing jamming. Okay? Then you may want to ask, why there is no collision? I really want to see collision, right? But why there's no collision? Okay, this is because our setting is like this. Yeah, we usually automotive company tend to be conservative. When we talk about this kind of system, the setting is gap and speeds are obtained by my own sensor, and we assume it's secure. Okay, and only acceleration are provided via V2S communication. Okay, so if I don't receive any information about acceleration, then I will assume the car in front of me will decelerate immediately. Okay, so that's the reason if I don't receive the information, I will become very conservative. So the car following gap will become longer. Then security is an endless game. Okay, if the system design is all of this information is based on V2X communication, then it's true that it is possible that maybe there will be a collision if you don't do any conservative approach. Or maybe the car will just stop, right? Because I don't receive any information. And someone will also argue, how can you guarantee that the data from sensor is secure? It is possible that an attacker approach your car, do some physical attack to change your sensor or something, then it is possible that this information is wrong. Yes, it is correct. It is possible to do that. But of course, the risk of attacker is higher, right? Because he or she needs to physically approach your car. Then maybe it's more difficult or higher risk for them. So we would like to say jamming is still the easiest way to do attack. Okay. Or there's another approach to hack this information, and you don't need to physically touch the car. Okay. What's the approach? For example, the air fighter, right? Their painting is very spatial. They will not reflect any radar signal, right? So if the car in front of you, they use a very expensive painting to paint the user painting to the button side of the vehicle, then your own sensor will be full. Then it is possible to create collision or not. But again, we believe the cost of the attacker is much higher. Then it is not the first priority for us to protect. Okay, so that's some discussion of this example. Okay, so talking about jamming, then let's take a look at another example is intersection management again. So this is video without jamming. So let's switch to this mode. This is a good scenario. If someone is jamming, yeah, again, I disappoint you. There's no collision. Yeah, but no one can go through the intersection. Okay, in this case, it's a little bit different from CSIE. It's very interesting that in this case, the attacker doesn't need to do too much thing to create this scenario. Yeah, it doesn't need to let you receive no message. It just needs to let you receive the message later. Okay, for example, I say the intersection manager may tell you to enter the intersection after 5 seconds, right? The attacker just needs to let you receive the message after 5.1 seconds. Then you cannot go through the intersection. Because we want to be conservative, right? Before receiving any confirmation from the intersection manager, I need to stop. Okay? Then, if I receive the message at 5.1 seconds, and it say, please enter the intersection 0.1 second before now, but I have stopped and I didn't catch the window, the timing window, then I need to stop and request again. And this may happen again and again. So in the worst case, no one can go through the intersection. And it seems to be very bad, right? The attacker doesn't need to work too hard. Just delay the message can create this scenario. But if you know the current network, communication network condition, somehow the intersection manager can be not that aggressive. Originally, you want to say scheduling the vehicle to enter the intersection at 5 seconds is the optimal solution, but somehow you can schedule it at 7 seconds, right? Then even the message delay, the vehicle receive it at 5.1 seconds, it still have 1.9 seconds to adjust its behavior. So in this case, although the performance is worse than the no jamming case, but at least we can let those vehicles to go through intersection. Okay, but here there's another argument that if the attacker is very smart, it gradually increase the network delay. Then in that case, I agree. Even we do something, the worst case is still no one can go through intersection. But again, that means the attacker must be very smart. And in the end, you still need to do very hard to jam every message. Okay, so this is talk about jamming. The next topic I would like to talk about security is game theory analysis. So when I was at Toyota, we discussed with people in Toyota headquarters, talk about security. They say if we separate attacker into outsider and insider, they are afraid of insider much more than outsider. Outsider means, yeah, you can use PKI or key exchange to protect against. But insider means then they can get the key. For example, a sensor is hacked. The data is wrong. Even the communication part, you have the authenticated key. It doesn't help. Or maybe the hardware or software flow is discovered or secret key is leaked, no matter during the manufacturing or design process or after market. Okay? So they want to protect against insider. And this is a roadmap. Okay, let's talk about message authentication. If there's no protection, then everyone can attack. To protect against outsider, we can use key sharing, no matter it's symmetric or asymmetric key. Okay, then for insider, key sharing doesn't help. Then we can use game theory, try to limit the motivation of attacker to do attack. But game theory can only be used for rational attacker. If the attacker just want to attack, no matter what, I don't care the cost, I just want to attack, then we will talk about intrusion detection. Then at this point, I would like to talk about game theory. So we will use intersection manager as an example again. Somehow we really like to use intersection management as our use case because actually this is a very fundamental or very representative application because it solves the fundamental problem, right? Two vehicles want to go through a conflict zone. Which one should go first? Yeah, that's the very fundamental problem. Okay. Game theory here. What's the scenario? If there are two vehicles approaching the intersection, one say my arrival time is 5 seconds from now. The other one say it's 4.8 seconds from now. Then the intersection manager very likely will schedule the one with 4.8 seconds first. First come, first go, right? Then the car with 5 seconds say, oh, the other vehicle say 4.8. Then I want to say 4.6. So the manager will schedule me first, right? Then the other car, 4.8, say, you say 4.6. Then I want to say 4.4. So this is a game between two vehicles. So we want to design some method to make sure they don't have motivation to lie. Okay? And our approach is using payment. So after this work, I realized that why there are so many game theorists, they can win Nobel Prize in economy. Because without payment, it's very difficult to solve this problem. We can only solve the problem for two vehicles only. With payment, we can generalize it to multiple vehicles. So let's show video again. The yellow car is coming, going to have dinner with friend. Red car is going to catch a flight. Yellow car will arrive earlier, but red car can pay yellow car to go through intersection earlier than yellow car. Okay, so it's like a little bit. Anyway, you can see that the one arrived which expected to arrive later can pay to go through the intersection earlier. Okay, and the most important property of this solution is regarding how much you want to pay to go through the intersection at certain time. This information, they will not lie. They will tell the truth. Because if you lie, you need to go through the intersection later, or you can go through the intersection earlier, but you need to pay much more than you want to pay. Okay, we can prove it reached the equilibrium, so they will not lie. Okay, so this is a very interesting example. And here, actually there's a tricky part here is someone, for example, you say, I have done of my research and homework, and I have nothing to do. Then I drive my car outside. At each intersection, I say, I want to be the last one, so I can earn money, right? But definitely this is not good for transportation design, right? We don't want to create unnecessary traffic. So actually, this is because our current setting is a zero-sum game. If we change a constant there, you can say this is a intersection text or something. And if you design the constant well, then we can limit the motivation of that case. Okay, and then maybe government can earn more money. So we can fix this problem. Okay, question?
So in this scenario, people who have more money don't have to wait in traffic.
Yeah, somehow it becomes this thing. So I agree. So this really depends on if you regard this intersection as it's a public property or it's like a capitalism solution. Yeah. So I agree. But here actually what we want to do is we want to use game theory to make sure they will not lie. Okay. So talking about game theory, so this is another very hot topic. And actually I started this work when I was at Toyota, and I have an intern who is super good at game theory. So this is very, very, very hot topic for machine learning, right? This is a stop sign. This adversary learning or classification, I add some tab, and the classifier will misclassify it. Okay, but here we are thinking a very different solution from machine learning people. Okay, we say we would like to add barcode to the traffic sign. This is different from general image recognition, right? If you say your image recognition want to recognize it is a dog or cat, you cannot catch the dog and cat and put barcode on it and do recognition, right? No, you cannot do that. But traffic sign is controlled by government. Okay, we can add barcode on it. But we didn't say we solved the problem. We just say with barcode we can do some analysis, use game theory analysis to provide a better worst case. So I will not go into the detail. Actually, but I should acknowledge that in turn that this story is his story. Okay, so they say the attacker is the army from it's Persian army. They want to fight with the 300, right? And the 300 is a classifier. Our resource is limited, and then we don't know what's the capability of the Persian army. Okay, so if you keep the original traffic sign, it's like they fight each other. They have the battle on the field, an open field. Then in this case, the 300 is a very bad, right? Because it's open field, then they will be defeated. But if we can limit the battlefield to a narrow valley, like the story, then the number difference will not become a major factor. Then in this case, we can do some analysis and make sure the worst case is better than fighting on the open field. So I think that's a philosophy behind this, so that we can limit the dimension of this problem. Because barcode is just white and black and one dimension, and its original problem is 2 dimension, and maybe they are different colors, so we can reduce the dimension a lot. So that's another use case. We can use game theory. Okay, continue this roadmap. After game theory, we still need to protect against irrational attacker. Then in this case, we can only consider intrusion detection. So basically, in this case, we use CSIE. We know that we can use some kind of different approaches, like physics rule, PCA, or hidden Markov model. And they can have different kind of capability to do detection, but they also have different kind of computational complexity, so that maybe some are applicable in car, some are applicable at edge or roadside unit. So we consider this kind of constraint. And here, when we say detected or non-detected, probably you can imagine it's not a 0-1 problem. Detected means detected, for example, 95%. And non-detected means probably we can only detect 5%. So that's intrusion detection leads to another problem is consensus. So if there are multiple detectors, they have different opinion about this report or this event. Can we combine different detectors' result and reach a better consensus? So, for example, if A say, I think the concept is if A says B is wrong, B is a bad guy, how do you know B is a bad guy? Maybe A is the bad guy. He say a good guy is a bad guy, right? So if we consider multiple vehicle, multiple detector, maybe we can run consensus algorithm and to have a better intrusion detection result. But consensus is not only for intrusion detection. Yeah, you can also use for example, if there's a traffic congestion at the intersection, or if there's an obstacle on the road, something like that. And again, consensus algorithm is a very famous problem in distributed system, but in automotive use case, we need to consider that timing is very important, and the vehicles are always moving. So that's very challenging properties or features. Okay, so that's about security. Many different kind of topics. So if you are interested in that, we can definitely talk more after this talk. So last topic is about automotive design automation. So I would like to use this term because actually my background is electronic design automation, means when you design circuit, you need some software to help your design because the design cost is super high. And as automotive systems become more and more complicated, I think this trend is happening to automotive system. Okay, talking about the design complexity, let's talk about software. I have some data say software value increased from 2% to 13% from 2000 to 2010. Unfortunately, I don't have the recent result. But do you remember what happened in 2010? 2010 or 2009 is the year that General Motors almost bankrupted. Okay, in that year, no one is. Maybe I should not say no one. In that year, most people don't think about connected vehicle, autonomous vehicle. They regard automotive industry as a sunset industry, right? At that time, software value is 13%. And as connected autonomous vehicle become popular and hotter, we believe the value is increasing. But different from, for example, you are writing a homework, maybe it's a sorting. If there's a bug, it's fine, right? Just deduct some point. Or you are writing some app, just get a 1 star comment from user. Different from then, the the correctness or safety or quality of automotive software is much more important than your homework or other application. Okay, so that's the reason we need some method to help us in the design. But talk about hardware. Okay, your vehicle is actually like a distributed system. There are at least 50 ECU like a CPU. They do some computation. Okay, do you know what is the frequency of the ECU on your car? It is, most of them is less than 100 megahertz. Very slow. Okay, so if you want to do some image recognition or some machine learning method, actually it's impossible to do it on current ECU in your car. Okay, so that's the reason automotive company are thinking some computational component like FPGA or GPU. But how can you guarantee they have no bug? The current ECU is so slow because sometimes slowest thing or simplest thing is safer, right? FPGA or GPU, they are very complicated. There's a risk, right? This is about computation. How about communication? Do you know the current in-vehicle network is controller area network? Its bandwidth is only about 500 kilobits per second. Okay, it's super slow. Okay, so automotive company are thinking Ethernet, but Ethernet cannot provide timing guarantee. So that's a big problem. So that's the reason automotive company will not use Ethernet for in-vehicle communication. Or even maybe the current autonomous function are using Ethernet, but remember the current, even Tesla, the driver still takes the responsibility, right? And the basic control is still based on control area network. So if you want to use Ethernet-based protocol for in-vehicle network, probably the next possible solution is time-sensitive networking. Okay, no matter how, what I want to say is software is very complicated, yeah, but hardware is very weak, or hardware cannot catch the trend, the development trend of software. So to design a car is not an easy thing. Yeah, you need to be very careful. There are timing, there are security, safety, reliability, robustness, performance, a lot of things you need to consider. So we need to check the system in very early design stage to make sure there's no bug or the system is correct. Then we can go to the next level, okay? Because implementation cost is super high. If you don't find a bug, or if you cannot guarantee safety or some property there, you find the bug or find some design error in this stage, or even aftermarket, the cost is super high. So that's the reason we believe we need some tool here, or need some systematic method to check safety or compatibility here. So similar thing, that's something I mentioned during the security part. We need to identify security threat as early as possible, and then we need to think about security requirement. We cannot add security after implementation. It's too late. Your system resource cannot match that. Okay, so this is the concept of design automation and the V model. So maybe you know that even Toyota's car or General Motors car, actually those components or subsystem is not built by themselves. They have tier 1 supplier or tier 2 supplier to provide those components and combine them as a final product. Okay, so that involves some compatibility problem. So this is still a problem I want to solve, but I have not solved. Is, for example, you are driving your car and it starts raining. When you start raining, you say, oh, it becomes more dangerous. Or autonomous car will think, oh, it becomes more dangerous. Then I want to increase the frequency of some software task. Yeah, dynamically. I mean, current car design, the frequency is always fixed. Okay, but in the future, maybe they want to increase the frequency depending on the environment. But can you really increase the frequency? Will it affect the timing of the switch of the in-vehicle network? We want to know. We want to provide safety and a guarantee to this system. So that's something I would like to do. So I worked with Professor Kang before for another use case. It's about subsystem compatibility. It's similar to the concept here. Okay, actually that's trigger another big concept is plug and play system. Means in the future when you buy your car, maybe you just buy a empty car. Empty car means software is empty. Then how can you build your car with software? In short, it's like your smartphone. You go to Toyota store to buy app and install on your car. So that's a more general concept of the previous slide that we want to very flexible to download, update, or activate your vehicles. So that's very fancy, but due to the time limit, I cannot go into detail, but there are so many challenges. For example, I want to execute one software program. Where to execute it? There are so many ECU on vehicle. You need to pick one to execute it, or you always pick the same one to execute it. Or you want to add your cloud server to have your execution. Or there are too many traffic, right? I mean network traffic and too many processing here. Maybe you can have edge server to help you to do those computation. Yeah, I think this is still very open question. Of course, there are some research problem there, a research paper or research progress there, but I believe it's still a very open research direction. Okay, I have quickly go through the many different topics. So for some ongoing work, this is just some very few examples for intersection management. Somehow you can imagine there are so many assumptions, so many simplifications. So we would like to explore more after this. And the security design analysis, we probably, I think consensus is still a lot work we can do. And the automotive design automation, so verification is definitely very important to guarantee something of your design. And we are very interested in a model called weekly hard model. Okay, this is the last slide. This is also very interesting. So this is a small self-driving car we built when we are in Toyota. Okay, we have LiDAR and we have camera to sense the distance to the obstacle. And you can see the gap is half of the parking space. When it stops, it's about 1/3 of the parking space. Okay? And we are engineers, so we want to do something to hack the system. So we unplug the LiDAR. Okay, now we have only camera to sense the distance. Okay, maybe you can imagine that what will happen. Yeah. Originally, when the car following the distance is about half of a parking space. Now you can see the distance is longer. It's 1 parking space. And when it stopped, originally it's 1/3 of a parking space. Now it's probably half of a parking space. Okay, then we unplug the camera again. Okay, what will happen? Can you imagine? If you want to find a job in an automotive company, please answer this correctly. No LiDAR, no camera. What this vehicle should do? Yes, not moving. Now you are qualified to be an automotive engineer. Yes, be conservative. Yeah. You cannot sense the distance. You don't move. Yes. Okay. What I want to say is we built this vehicle probably 2.5 thousand US dollar, and the LiDAR here, small one, is 1.5 thousand. Yeah, LiDAR is very expensive. And this LiDAR is actually probably only sense the distance, probably 5 meters and probably 180 degrees. You cannot use this in a real car, okay? So that's the reason when we talk about when will autonomous driving become reality. So cost is a problem, okay? But I believe as the technology advances, cost will become lower and lower. And the first item, technology. My personal feeling is current autonomous technology is safer than human driver already. Okay, because human drivers are super dangerous. They will drunk driving. They will play Pokemon Go during driving. Yeah, but autonomous driving will not do that. So I say it's safer than human driver, but it doesn't mean it will become reality, because even it's safer doesn't mean people will accept it, right? And the second item is cost. Next one is law and regulation. This is probably not technical, but we need law and regulation to figure out if something bad happened, who should take the responsibility, right? This is the reason that even it is safer, we cannot make it real at this point. Make it real means not assistant, means you can sleep when you get down the car, okay? Next one is human comfort. So intersection management, the first video I showed, super efficient, no collision. But if you are inside the car, you will see a car driving towards you. I cannot. I don't feel good about that. So that's human comfort. And the last one is philosophy. Yeah, I mean, yeah, even it's safer, but it's not fun, right? I mean, sometimes driving is fun. Or this is something it's really difficult to change because someone just think cars should be driven by human. Then you want to ask them to accept it's driven by machine. Even it's safer, some people just cannot accept. Even myself, probably I will also hesitate to accept it. So if someone asks when it will become reality, I also got the same answer with many engineers in Toyota. I have to say, automotive companies are usually more conservative. And the Toyota is more conservative than other automotive company. So when I was a Toyota, probably the answer we got is 30 years from now. But it's, okay, maybe I should say 27 years from now, because 3 years ago they said 30 years. Okay, but somehow I agree, still a long way to go. Yeah, not only technology, but also cost or other method. Yeah, and then security is also a big problem, right? Okay, so that's everything I have today. So thank you very much. So if you have any question, I'm happy to answer your question. Okay.
Talk about this intersection manager management sort of use case.
Yes.
Do you see the potential of moving sensory to a centralized solution as well?
You mean
perception? Just,
perception?
Yeah, just don't put sensors and perception system on the car anymore.
I think it is possible. I mean, currently, the information I need is actually just from vehicles. So when I say intersection centralized solution, means the decision is centralized, but those sensor information is provided by vehicle. But it's true that it can also be done roadside unit. Yeah, so it really depends on what kind of design you want to have. So my personal feeling is big intersection, you can have roadside unit, intersection manager, to support the intersection management. But for small intersection, like four-way stop sign, and nowhere, probably we don't need any manager or roadside unit. We just let vehicle to communicate with each other and use a distributed solution. Yeah, that's my feeling. Yeah. Okay.
You also said that for intersection management, usually use a heuristic approach instead of optimization based. Is that due to the lack of computation power on the vehicles, or just
Okay, so I think the most important thing is still real-time constraint. We want to make the decision as early as possible, or at least within 1 second or like that. And yes, if it is distributed solution, the problem becomes more severe. I mean, the computational resource is really, really limited on vehicle. But if you are talking about intersection manager, because it's a roadside unit, so I think that can be much more powerful. Yeah, so that similar question, right? If it's a super big intersection, probably it's a bottleneck of traffic, right? Then probably it's worth to have a powerful intersection manager to solve the problem. But if it is a four-way stop sign, no traffic usually, then of course I don't want to have a powerful manager, or even I don't want to have a manager. Yeah, so it's really, yes, we need a real-time decision, but regarding the cost or something, probably it really depends on what kind of intersection you have. Yes.
I guess the cost of the computation power, which is safe, is too high to implement in every vehicle?
Every vehicle probably is too much. Yeah. And that's another problem, that when you say cost, yes, very powerful computational unit, cost is a problem. Another problem is robustness. Yeah, very powerful means very complicated usually, or very complicated. But automotive company want to make sure it's as simple as possible, but it's robust and safe. It's correct. So sometimes maybe you can hear some news, oh, there's a bug in the compiler or some kind of bug in the architecture, something like that. Automotive company don't want this happen. Yeah. Yes.
So you talked about designing algorithms that are computationally efficient and can run in real time, but
Yeah.
If you guys don't think that autonomous vehicles on the road are going to be reality for 25, 30 years, for that time, they will look like nothing. So have you considered stuff like that?
Okay, you mean after 25 years, maybe the computational ability is much more powerful, right? Yeah, I agree. But probably not in a short time. Yeah, it's still a lot of time to let every vehicle to have very powerful computational unit. I mean, to production level. I mean, of course, all automotive companies, they are building their autonomous vehicle right now. Their computational resource is, I think, it's quite good already. But talking about production and reduce the cost that human or people wants to buy, then that's another story, I think. Yeah, that's my observation. Yeah.
Okay, since time is up, I have to keep the discussion offline, and thanks for today.
Okay, thank you.